did we talk about? Two different things, I guess. Who's going first?
It's about logs.
Talked about the logarithm, and then we talked about dimensions. So the key with the logs was that we could convert exponents into, so we could convert multiplication into addition, and so exponents into coefficients. And that turns out to be really useful when we think about dimensions, when in a way that we're going to do another example right now. We'll see that happen again. Then there's this fancy theorem, which I just realized looking through the notes, I am not explaining at all in a comprehensible way. So I need to make it a more explicit version of how it is, because the notation is terrible, and also, even if the notation was good, the words I'm saying don't seem to make any sense in the order they're presented. So maybe they're the right words, they're in the wrong order or something. Anyway, I'll try and explain what that means in a very concrete example, and we'll look at the theorem, but I don't think, we'll look at the results of the theorem, but I don't think that we have to do we shouldn't redo the derivation based on this version of the notes, which is just confusing. But then we'll start talking about partial and total derivatives, which hopefully will be a reminder for everybody, but that's the last thing we have to do for this week. Does that make sense to everybody? Okay. So what were some of the key ideas about dimensions and units that we had yesterday? What is a dimension? What's a unit? What's an example of a dimension? Maybe that's easier. A length, or a time, or a intensity of, an ampere. They're funny kind of things, some of them. Normally in geophysical situations, we're dealing with lengths, times, masses. Those are the key ones that will come up most often. Sometimes temperature. Okay, what about, so then what's a unit? Yeah, so it's like the marks on a ruler. It's the thing that you're measuring relative to. And at the end of the day, yesterday we talked about making a dimensionless equation that was based on units that were kind of natural for the problem. So we talked a little bit about the depth of the ocean being one possibility, but you could use anything that was convenient and measure in units of that. So I might measure the air in this room based on the width of the room. That would be an interesting way to measure the volume. Is, if I have this width, then I could cube it, and that would be sort of the volume of the room. Or I could take the height of the room and measure it that way. Or I could take the RMS temperature variations in this room, if I could measure them, thermometer, and use that to be my standard of temperature. So temperature deviations. So whatever is convenient for the problem you're having is one way to pick units. The other way to pick units is to use something like the SI system or the CGS system and just take standards and measure everything against those standards. So why is dimensional analysis powerful? Like, what is it that really makes this whole, why is this worth talking about? It seems kind of silly, like, didn't we all learn this long ago? There's one subtle point that we started to talk about yesterday. Yeah.
Like, if you pick like numbers that scaling numbers that make sense for the system, then like relatively speaking, like the variables themselves are like sort of have equal weight, and then like the weight of the individual terms is based on like the value of like that dimensionless coefficient in front of it.
Absolutely. So if we do know the equation we're writing down, we can guess how big the different terms are if we have a good guess for the units, the natural units of the problem. That might allow us to simplify the equation. We also know that the real system can't depend on our arbitrary choice of units. So we had all these rules, like you can't set one dimension equals a different dimension, and you should be, if you convert among units, you can multiply by a conversion factor and switch from one to the other. So those kind of manipulations are reminding us that the real world doesn't care how we measure things. The real world has its own way of measuring things. Our convenient measurements are what's convenient for us observationally, but it can't, but the result of the experiment can't depend on our convenience. So those key pieces are coming through. So there's actually one more thing, which is kind of taking those to the logical extreme. So I'm going to do the example in the notes about how fast the sailboat goes, which I think is a fun example for a particular reason. Well, because I like sailboats. So. All right, so how fast does a sailboat of a certain length go? There's water, there's waves on it, there's a boat. Or you can make it whatever kind of fancy sailboat you want. Lots of, like a pirate ship. And it has a length. And it has a speed, I guess. What else might that depend on? Well, first of all, the units, the dimensions of lengths are length. Dimensions of speed are length per time. That's something. What else might this depend on? What are some properties that you might think were important?
The water velocity.
The water velocity is one. And over time. That was actually a cool. Well, this isn't normally part of the story, but you can put it in. It's actually pretty sort of easy to do.
The wind.
The wind speed, maybe. So I'm writing the wind stress, which has units of density times the velocity squared, which is mass per length cubed times length per time, length squared per time squared. What are about the properties of the water? Yeah.
There's friction between them.
So we might have something like the viscosity of the water to capture the friction. We know that's a property of the water. Let me use this viscosity. So this is the dynamic viscosity, which is the kinematic viscosity times the density. So this guy has units of mass per volume, and this guy has units of length squared per time.
What is that again?
Sorry, this is the what's called the dynamic viscosity, and this is called the kinematic viscosity. This one depends on the mass of the density of the fluid, and this one doesn't. So they're just two different ways of thinking about the viscosity. It doesn't really matter in water because the density is almost constant, so you can just relate those two to each other, but it's something that's very rarefied, like a gas. You might use this one instead. You might be careful about this one because you can't be viscous if there's not any stuff there. So, but I like this one because there's a mass in it. We're going to see how that goes. And then, well, obviously we also have the density of water, and let's just assume that it's constant to keep our lives simple, even though it's not constant. There is actually a really cool effect called dead water. All right, this is going way off the topic. But anyway, if you're in a boat and you go over a fresh layer sitting on top of a salty layer, like if you go into a fjord where the glaciers are melting, you'll actually start making waves on the interface between the salty and the dense water. And so even though the surface looks flat, you actually slow down as those waves start extracting energy from the boat, which is a cool thing. Anyway, one thing I just hinted at though, the waves can take away energy from the probably need something about the waves in there. So why are there waves on the surface of the ocean? There's wind, so we got the wind in there. And what makes them not just get bigger and bigger and bigger? Gravity. So we probably want the acceleration due to gravity as well. Okay. So let me put aside this one for the moment. We'll come back to that one in a second. And let's think about all these other ones. So what we want to write is we want to write an equation like speed equals some kind of function of all those things. Right? That would be like the ideal. So what can we say about that equation without knowing anything about it, really? Or just, what can we say about that based on yesterday's discussion? The units have to work. So the units of this and the units of that have to be the same. And that greatly limits what we can do with all these parameters. So I can't write C equals L, because the units are wrong. But I could write some kind of generic formula, I could write some kind of generic formula which was a product of all of these things. I could say G to some power A times L to some power B times, let me leave you out for a second, times mu to some power C times rho to some power D. Okay, let me put these two aside for a minute. We'll come back to those in a second. Well, actually we can tell what this one is. And then we already need the viscosity. Am I good? Oh yeah, already got the viscosity. So if the water is moving, and the boat is receiving a certain amount of force from the wind, or however, do you think that if the wind goes away, how fast does the boat move? Does it sit still? It moves at the water velocity. And if it's going upstream, it should add to the velocity, it should slow it down, and if it's going downstream, it should speed it up, right? So it turns out that the only thing that's important is going to be the speed relative to the water. So this concept is called Galilean Invariance, and it essentially means that you should only be, I need to go into the frame of reference that's the important one. And in this case, nothing's going to happen to the boat if it's sitting still in the water, but if the water starts moving, you're always relative to the speed of the water is the speed you want to have. So this one we'll pull out aside, and so we won't actually write C equals some function of those, we'll write C minus U equals some function of those. And that'll be the place that we have U in. And we could put U in on this side, but going through the logic of the relative part, it would end up being like this, because it has the same units, and then it would come back like this. And so that's taken care of. And the wind speed I want to leave aside, we'll come back to that in a second. Okay, so knowing now the dimensions of these things, what can you say about these coefficients? I could write the dimensional equation L over time equals G, which has units length over time squared, which is the A. L, which has units of L, which is the B. Mu, which has units of mass over length cubed, length squared over time, to the C. Density, which has units of mass over length cubed, to the D. Right? That's all. That has to work as long as our function is some kind of function like this. We could have like some complicated function where you had multiple terms added together that were different ratios of this thing, but all of them would have to have the same unit. So if we did this once and for all, we could then take different forms of it and add it on. So it doesn't have to be a product as our answer. It turns out for this one that it is. So what's the constraint then on A, B, C, and D? How many powers of L am I supposed to end up with? 1. So there's an equation for L that says 1 equals A plus B plus minus C. Those two cancel, so there's an L downstairs. Minus 3 times D. Everybody see that? What's my equation for T? So I do the same thing for T. What do I start with on the left side? -1 is the power of T. What's the first one? -2A. Does B have it appear in this equation? And what about C? -C. And what about D? Doesn't appear. What about M?
0.
I've got zero M's on that side, and how many M's do I have on this side? I've got 1 for C, and I've got 1 for D. Okay. What kind of system of equations is this? It's a linear set of equations, just like we have been talking about how we solved last week. And we could have actually gotten it from here really fast if we had taken the logarithm. This is like the logarithm, because this is canceling the exponents of all the powers of those things. So this is related to the logarithm in some funny way. Can we solve this set of equations? How many unknowns are there? 4. How many equations are there? 3. So we can't get in a unique solution, but we can do something with this. We can reduce the number of possibilities, right? So how do we want to do this? Do we want to do this as a matrix equation? Do we want to just solve it? Let's just solve it by hand. We'll do it the old fashioned. Okay, so what does this equation tell you? So C equals -D, which means when we go back up here, this dynamic viscosity never appears independently of the density. C equals -D, which means we could have written this like this, or we could have just written it as the kinematic viscosity to begin with. So everybody see how that works? So the reason why we have the kinematic viscosity is because that happens a lot, that cancels out in these kind of systems. But maybe rather than mess it up. So this tells us that mu goes over to nu. Okay? So if C is equal to D, can I use that information to simplify this equation? Not really, because I've only got C there, and I can switch the C for D, but that doesn't really gain me much. But I can use it to simplify this equation, right? I can eliminate D from here. So which is equal to A plus B minus C, but C is equal to minus D, so that's plus C, 2C. Okay. And then I can go one step further. I can use this equation to eliminate C. So that tells me that C equals minus 2A. C equals, I get that right?
Plus one.
Plus 1. Okay, so then that goes over to A plus B plus minus 4A plus 2 equals 1. So minus 3A plus B equals minus 1, or B equals 3A. Alright, so we've got a relationship between B and A that's important. We've got a relationship between C and D that's important. And we've got a relationship between C and A that's important. So, have we boiled this down to being something that's unique? Now, so this is a part in the dimensional analysis where you say, oh right, but I understand linear systems. I have some choices to make. I could pick, what this is telling me is that on the AB plane, I have a whole range of solutions that are possible. I've got a full line of possibilities. I can just pick one and use that, and then I know the others would be a multiple of that. So, one that we could pick is A equals 1, and then what do we get? B equals 2. I didn't get that one right. Well, there's one in particular I want to get, which is why I'm trying to get it right. Oh. So what does that tell me? That tells me that a factor of G times L. I made a mistake. Alright, I definitely made a mistake because it's not what I'm supposed to get. Oh no, it's still right. Actually, let me make this one step easier. What if, how viscous is the water? Or how viscous is water? Not very. I mean, you can kind of push things through it. So, we could either think that the viscosity is really important, or maybe we think that gravity is really important. What would happen if we decided to neglect the viscosity? How would I express that in terms of C's? Didn't want it to depend on the viscosity at all.
C to be 0.
Yeah, so I could set C to be 0. If I do that, if C equals 0, then what's A? And then what's B? Sorry. 3 has minus 1. 3 has minus 1 equals 1 half. Then what's my function? C minus U equals, can the density appear if the viscosity doesn't? It can't, because we already had this C equals minus D. So both of those terms have gone away. They're both to the 0th power. Could there be something else? And I write this as equals. Let's think about that before we go back to putting the viscosity back in. What can I say? Can I say those are equal to each other? What if I multiplied this by 2? Would it change the answer? I mean, any of the logic? I could say this was 2 times something. Or I could say it was 10 times something. Right? That doesn't change the units or the dimensions at all. In fact, I could say, in general, C minus U over the square root of GL equals a constant. I don't know what that constant is. How do I know? Why am I saying it's a constant? So it could be a number. It could be any number we want. It could be pi, it could be 10, it could be whatever. How would I figure out what that number is? Like if I actually had a boat. You just measure it, right? I could go and I could say, well, how fast does the boat go? And how big is this number? Does that make sense to everybody? All right. It turns out that number is very close to 1, but I wouldn't know that offhand. If that number was equal, even if that number wasn't equal to 1, does this have to work if I compare 2 boats with different lengths? It does, up to some, like, maybe the boats have different shapes or something that might affect their flow speed or something. But if they were the same boat, just a bigger one and a smaller one, so they were dynamically similar, then this can't depend, as long as we're neglecting viscosity, this answer can't depend on anything other than that factor. Because we thought about all the things we can include, and then this is the only piece that we can come up with. So that's pretty cool. We just figured out how fast different lengths of boats go, without knowing anything about different lengths of boats. We don't know the number of how fast they go, but we know how fast they go relative to one another, based on their lengths. We could also talk about going to a different planet. And if water had the same viscosity, we might, the same kind of properties, we might change G by going to Mars and making it, is it 1/4? I think it's about 1/4 what it is on Earth. Maybe it's bigger than that. Whatever, I don't remember what it is on Mars. But we could sail boats around on Mars if there was water. And then we would be able to guess what their speed was too. So the power of the dynamical analysis is that we kind of got some kind of an answer right off the bat by just thinking about the possibilities in an assumed form of solution. Okay, what if we had neglected G instead, and then gone just the viscosity side. So what if we say that if A equals 0, so forget about gravity, what do we get if we go back to these set of equations? If A is 0, then what's B? 1. What if B is A is 0, what's C? C equals 1, and D equals -1. So what's that ratio? That says that C minus U equals viscosity mu over rho times 1 over L. I guess I should just say proportions. Or, if I rearrange this a little, the Reynolds number, C minus U times L over mu over rho, is a constant. So this funny combination of things, it's not obvious what I would end up with, but the Reynolds number, as we talked about last time, is a dimensionless thing. It's a speed times a length over a viscosity. And if it's dimensionless, it can't be equal to any other of the parameters in the problem. It could only be equal to like a number, a constant. This one has a funny name too. This is actually called the Froude number. This is the speed of the boat over the speed of the waves, which isn't obvious at all without knowing more about the waves, but that's the way it goes. So, okay, these are a number. Do they have to be the same number for every single boat? How could they be? What kinds of boats would they work for? Like what would violate our assumptions in this problem?
So we were talking about a sailboat, so the wind is like helping the sailboat.
Right, so if we had a motorboat or a different kind of power or just a different shape of boat, we would have other dimensional parameters that would tell us about that shape somehow. Like we might have the height of the mast, or we might have the horsepower of the motor, something like that. We would have had other parameters in the problem that we didn't have. But if we don't have those, this is an interesting thing about the boat. At whatever speed it's traveling, it's Froude number. This is an interesting thing about the boat, it's Reynolds number. It turns out in this problem that both of these act more as limiters for the speed of the boat. They're like they set sort of the maximum speed that the boat is likely to go before it starts feeling either the effects of viscosity very strongly or the effects of losing a lot of energy by producing waves. This one turns out to be the limit for boats of normal size. This one is really important for tiny boats. Because so there's a length scale in here, and there's a length scale in here, and viscosity is more important at smaller scales than it is at bigger scales. So it turns out this is the one that actually limits the speed of boats. Yeah.
We're just talking about the dimensions here. Why is it? Well, how do we know that the length is something that's actually significant? Because could we also have the width and the height?
We could have the width, we could have the height, we could have the volume of displaced water, we could have a lot of different things. Exactly. So that's exactly what I mean is I've played fast and loose by starting with just the length here. Because I knew where I was going with the Froude number. If you put the width in, then you might expect that wider boats go slower than narrower boats. And that actually would come out. So up to a point, but this is the length this length really isn't the length of the boat so much as it's the wavelength of the waves that the boat produces. So we didn't know that. We couldn't possibly know that by this dimensional analysis. But that's the kind of thing that you could go and test. You could say, oh, if I run boats with the same length and different widths, do they go different speeds? It's not actually as much as you might think, because what really is the important thing is the wavelength of the waves they produce in their wake is actually the controlling parameter, not really the shape of the boat. Does that make sense? Or, I mean, it's a surprising thing. Okay. So, this is kind of an interesting example. So what fuel did we use? We took our set of parameters, we figured out how many dimensions were in them, we set up this assumed solution, and then we looked for things that were dimensionless ratios. Here we have the Fruit number, here we have the Reynolds number, and we talked about the two limits where either one of them was important and the other was negligible. And in that limit, we got Fruit number equals a constant, or Reynolds number equals a constant. More generally, we could have said there is a constant that's equal to some function of the Fruit number and the Reynolds number together. So regardless of how big they are, I could write a function like that and say that that was the most general thing I could have done to describe this particular set of parameters and still be dimensionally consistent. Okay, so I'm going to erase all this, and then we're going to talk about the general property of Buckingham Pi Theorem. So the Buckingham Pi Theorem helps you count how many of these things you're likely to get from a given problem. And I go through the proof in the notes very poorly. But it's basically setting up the general linear kind of system that you get, and then seeing how many solutions it could possibly have, and then thinking about that. That's the process. So, the version of the Buckingham Pi Theorem in the note says, if you are given, if there's a physical problem with p dimensional parameters, and R dimensional results, and D dimensions, there will be at most P plus R minus D independent dimensionless parameters. Okay, so all these are just funny words. What were these in this example? How many dimensional parameters do we have? G and L, and mu and rho. And we took C minus U together. So we had 4 of these. How many dimensional results were we looking for? Just this one, C minus U. We were looking for speed. 1, which was C minus U. Rho, G, mu. How many dimensions do we have? So it's kind of like, how many different things appeared in this equation? 3, length, time, and mass. Okay, so what is P plus R minus D? P plus R minus D. 4 plus 1 minus 3. Copy the answer. 2. Fruit number. Reynolds. those were the two we found. Which was C minus U over the square root of GL. C minus U times length over U over the. So, what was stopping me from taking fruit number squared and then fruit number times Reynolds number as my dimensionless parameters? Nothing really, right? At the end, I just said, let's suppose that, G equals a half, and off we went. Right? Because I had that whole linear subspace. We had 4 unknowns and 3 equations. We could have changed the answers and slid things around. We could have made the powers in this go up. Like I could have actually had fruit number to any power n I wanted, and Reynolds number to any power n I wanted, or their product, or their ratio, and all of those would have still solved those equations. Independent. So these are independent in the sense of linearly independent in those equations for the exponents. So all those examples are not linearly independent. They're all just new combinations of the possible solutions to that set for the exponents. So those are all possible. I directed us toward these two because these two are ones that have names. The same way, and this one we said had a name because it appears in a particular term in the equations yesterday, Monday. This one also appears in a particular different set of equations, and so it's got a name. So I knew I was looking for these two, but it actually wouldn't have changed the way I interpret the problem very much if I had ended up with them to a different power. I just would have said fruit number squared is equal to a constant, which is the same thing as saying fruit number is equal to a constant. Everybody get all that? So then, okay, so we can do this Buckingham Pi. It's called the Pi theorem because pi is the symbol for multiplication, like this. So this is a pi base, it's multiplying things together. So pi is in there, so it's if you like, it's the Buckingham multiplication theorem, because it's counting of the number of multiples that have the right units. So then what did we do when we got these two? We said, let's suppose we just forget this one for a while, just think about this one. Or then we said, forget this one for a while, just think about this one. So if you go through this procedure and the number of independent dimensionless parameters comes out to 1, then we say that 1 is equal to a constant. That's the only possible solution. For all those reasons of what we went through, like big boats, little boats, if you want to make them different boats, you need more parameters, and that would have changed the number. But if you go through this procedure and end up with only one answer, that dimensionless parameter must equal a constant. That's the only possibility, given that set of parameters. If you have 2 of them, they can be a function of each other. If you had 3 of them, they can be a function of each other. And so now you can see that the more of these independent parameters you have, the more complicated the world can be. Okay? So the homeworks go through a couple more examples of doing this kind of thing, on just problems where you can think through all of the possible parameters, and it's amazing how far you can go. This is without knowing any of the theory behind fluid dynamics at all, really, just knowing that there are these parameters. So it's a really powerful thing. So on top of scaling the equations, on top of knowing dimensions equals dimensions in the equations, this is a consequence of that, thinking about the dimensions thing. You have to express your equations in some sense in a dimensionless form, and in certain kinds of problems where the number of dimensional parameters is small, the kinds of solutions are also very small. Does that make sense? Is that right? So the one thing we didn't talk about was the wind stress. So what would you, can anybody see a dimensionless parameter that's easy to think about out of the wind stress? I could have put it in again, I would have gone through this machinery. I would have had one more dimensional parameter, so I would have had 5 plus 1 minus 3. I would have had 3 dimensionless parameters. Anybody see a convenient one based on what this looks like? Over row has the units of velocity squared. So I could have come up with C minus U over tau over rho square root. So this is the expected relationship in speed of the boat as the wind speed changes. So if I wasn't changing the wind speed, I would have expected to see one of those, the gravity waves, the waves would have suppressed it. But if I slow down my wind speed or speed up my wind speed, I could actually go slower than that speed based on this kind of a scale. And I know that it's the square root of the wind stress that counts, because not the wind stress itself, because of the dimensional analysis. Okay? All right, so are there any questions on this? Because we have run out of time. So we'll do PDEs and ODEs on Friday. Yeah.
How did you see that? Is there an easy way to see that
Um,
going through it?
This, so even to remember the units of wind stress, I wrote it as a density times the velocity squared. So this velocity is called the friction velocity, and it's just a rescaling of this. So because that comes out a lot, that you have things that are a velocity versus the friction velocity, I knew I was gonna get that, essentially. But I could have also gotten something more complicated, because I could have multiplied this by Reynolds number and it still would have been dimensionless. It would have been another way to express tau in there. So I could have come up with other ones. I knew this one was a good one. So this is a funny thing. This doesn't tell you which parameters to pick. It just tells you how many you need to find. And so after you're familiar with these kind of problems a little bit, you look for the ones that you know to expect, which are the ones that appear as like the coefficients in the scaling of the equation that we saw yesterday. But before you get started, you don't know what to expect. You just come up with whatever solves those equations, and that'll be fine. Then after you do some experiments, you can maybe improve on that, because you'd like them to be the most manageable things to work with. So the ones that have people's names on them are manageable in one system or another. Frequently, actually, some of them are redundant with one another. The Froude number is actually equal to 1 over the Richardson number squared under a lot of circumstances. So they're not independent at all, they're just different definitions for the same thing. But Richardson was thinking about it in a certain kind of problems, Froude was thinking about it in different kind of problems. Doesn't matter so much that they're the same. Yeah?
What makes something independent dimension?
What makes something?
Dimensional parameter independent? Is it just that it's equal to a constant, or is it?
So it's in the linear set of equations. These are like the basis functions for the space of, so, wow, I just erased it. So if I had like the A axis and the B axis, and I had my relationship between A and B that I had found that was like this, I needed to measure along this direction somehow, but I just needed like a unit vector along that direction. And so what these are is they're like the unit steps along those. And so they're independent, they're linearly independent, like the solutions of an equation might be linearly independent, or the different equations might be linearly independent from one another. So they're going in different directions. If I had a different one going in this direction, say, then I might choose one in this direction for one, and one in this direction for the other. But what it means is I can't write one of them in terms of the other. These are actually different. This one's got G in it, and this one doesn't. So I can't make them a function of each other. If I could, then they would be dependent. But I can't. But I could have made other choices that also would have had that property. Does that answer it? Okay. So the homework will help a little, and we'll keep seeing these kind of things, and you'll see how they do. and you can go listen to the video, and after that, you can see whatever I've said, funny things.